You ever look at your computer's specs and see a bunch of different terms? You got RAM, you got an SSD, you got something called cache. It's kind of weird, right? It feels like your machine has a whole collection of different memories. So why not just one? Let's get into it.
So yeah, that's the big question. Why not just have one massive, super fast memory for everything? I mean, your phone does it, your laptop does it. Even the biggest servers in the world have this complicated setup. Well, the answer comes down to this fundamental trade-off that engineers have been wrestling with for, ever.
And here it is, the big one. In the world of computer memory, it's like that old saying, fast, good, or cheap. Pick two. You can have memory that's fast and big, but it'll cost a fortune. You can have it big and cheap, but man, will it be slow. Or you can have it fast and cheap, but you'll only get a tiny little bit. You just can't have all three. So instead of trying to find a unicorn, computer architects got clever. They decided to build a team.
All right, so let's meet the players on this team. Each one has a very specific job to do, and how well they work together is everything when it comes to giving you that snappy, smooth experience you want from your computer.
Okay, to make all this make sense, we're going to use an analogy. Let's imagine your computer's processor, the CPU, its brain, is a really busy worker sitting at a desk. Their whole job is to process information, but to do that, they need to get the information from somewhere, and that's where our memory team comes into play.
So let's break down this workspace. The fastest memory of all is called registers. That's like having a sticky note right on your desk. It's instant, but you can only write a tiny bit on it. Next up is the cache. Think of that as your desk drawer. Super fast to open, but still pretty small. Then you have your main memory, or RAM. That's the big filing cabinet over in the corner of the office. It holds a lot, and it's pretty fast to get to. And finally, you have your SSD or hard drive. That's like a giant archive warehouse down the street. It holds everything, but it takes a while to drive over there and get something.
Now there's another really crucial difference here, and it's called volatility. Think about that filing cabinet, your RAM. It has a weird quirk. The second you turn the power off, poof, everything inside just vanishes. It's volatile. That is exactly why you need the non-volatile warehouse, your SSD, to permanently store your operating system, your photos, all your important stuff.
And just a quick side note on why RAM is so much faster. It's all about random access. That just means the CPU can instantly jump to any piece of information it wants, just like you can grab any file from your cabinet. Compare that to old-school tech like a cassette tape, which was sequential. You had to literally fast-forward or rewind to the whole thing to find your song. That random accessibility, it's a total game-changer for speed.
So you have this team of specialists, right? Some are fast but small, others are huge but slow. How do you possibly organize them? Well, you build a hierarchy, a pyramid of power that brilliantly solves that whole speed versus size problem.
Let's build this pyramid from the ground up. At the very bottom, you've got the massive foundation, your slow warehouse, the external memory. A step up from that is the much faster filing cabinet, your RAM. Getting closer still is the incredibly fast desk drawer, the cache. And right at the very peak, practically part of the worker themselves, are the registers, the information sitting right on the desk. And look, the speed difference between these layers is not small. It is absolutely staggering. If getting data from the cache is like blinking your eye, then going to RAM is like getting up and walking across the room. But fetching something from the SSD, that's like a multi-hour trip to that warehouse. The jump in access time is just enormous.
So what's the whole point of this complicated pyramid? It's to perform a magic trick. The entire system is designed to fool the CPU. It works to create the illusion that our worker has access to one single perfect memory, one that's as massive as the warehouse, but as lightning fast as the desk drawer. So how does it pull off this incredible trick? Well, it all comes down to a really simple but powerful observation about how computers and, frankly, how we tend to work. Let's follow a single request for data and see what happens.
The secret sauce has a fancy name, locality of reference. But it's a super simple idea. It just means two things. First, if you just used a piece of data, you're probably going to need to use it again really soon. And second, if you just used a piece of data, you're probably going to need the data that was stored right next to it. That's it. That simple principle is what makes this entire pyramid system work.
All right, picture it. Our worker, the CPU, needs a specific piece of information to do its job. So what does it do? Where does it look first?
It's not going to go on that long trip to the warehouse, not yet. It's efficient. It checks the absolute fastest, closest, most convenient place first, right there in the desk drawer, the cache. And in the best case scenario, jackpot, we have a cache hit. The data it needs is right there. It's retrieved almost instantly,
with basically no delay. And get this happens over 90% of the time in a modern computer, which is a huge part of why they feel so snappy.
But what about that other 10% of the time? What happens when the worker opens the desk drawer and the information it needs just isn't there?
Well, that is called a cache miss. And now everything has to pause for a moment while the CPU takes that longer walk over to the filing cabinet to the RAM to find what it's looking for. This introduces a tiny stutter, a little delay in performance.
But here's the really clever part. When the system goes and gets that data from RAM, it doesn't just grab that one single piece of information. No. Remembering our locality principle, it grabs the data it needed plus a bunch of its neighbors, and it copies that whole chunk into the cache. It's making a smart bet that the CPU is going to need that neighboring data next, and that bet usually pays off.
This whole elegant pyramid structure has served us incredibly well for decades. But the thirst for more data and faster speeds never, ever stops. So this engineering challenge is constantly changing, and what's on the horizon looks pretty exciting.
We're seeing some wild new technologies that could totally blur the lines between these layers. Imagine memory that's as fast as RAM, but it doesn't forget everything when you power down. Or memory chips that are stacked vertically, in 3D, for incredible density. There's even this futuristic idea called in-memory computing, where you stop shuffling data around and just process it right where it lives. That would change everything.
So it all comes down to this. As our data needs just explode for things like AI, virtual reality, and massive scientific research, can these new technologies actually keep up? The quest for that perfect information workspace, one that's infinite and instant, it continues, and it is without a doubt one of the most critical battles in the entire future of computing.